Nuclear fission is the fundamental process that powers atomic weapons. The process begins with a fissile material, such as uranium-235. This heavy nucleus contains protons and neutrons bound together by strong nuclear forces. A neutron approaches the uranium nucleus at high speed. When the neutron strikes the nucleus, it becomes unstable. The nucleus splits into two smaller fragments, releasing a tremendous amount of energy and additional neutrons. The released neutrons can then strike other uranium nuclei, causing them to fission as well. This creates a chain reaction where each fission produces more neutrons, leading to an exponential increase in the number of fissions. For a chain reaction to sustain itself, there must be enough fissile material present. This is called the critical mass. Below critical mass, the reaction dies out. At critical mass, it sustains. Above critical mass, it becomes uncontrolled. Nuclear fusion powers the most destructive weapons ever created. Nuclear fusion is the process where light atomic nuclei combine to form heavier nuclei, releasing enormous energy. In thermonuclear weapons, isotopes of hydrogen, deuterium, and tritium are forced together to create helium. Watch as deuterium and tritium nuclei approach and combine. The Teller-Ulam design employs a two-stage process where fission initiates fusion. This multi-stage design allows for yields millions of times greater than fission-only weapons. Nuclear fission weapons employ two primary design approaches, the gun-type mechanism and the implosion-type mechanism. These designs differ in how they assemble subcritical masses of fissile material to achieve supercriticality and initiate the chain reaction. The gun-type design, exemplified by the little boy weapon deployed over Hiroshima, employs a straightforward mechanism. A subcritical projectile of uranium-235 is propelled by conventional explosives down a gun barrel toward a stationary subcritical target mass. Upon impact, the two masses combine to form a supercritical assembly, triggering the fission chain reaction. The implosion-type design, utilized in the Fat Man weapon over Nagasaki, employs a more sophisticated approach. A subcritical sphere of plutonium-239 is surrounded by conventional high explosives. When detonated simultaneously from multiple points, these explosives compress the fissile material inward, creating a supercritical mass and initiating the chain reaction. This design requires precise timing and symmetry for optimal performance. The implosion-type design proves far more efficient than its gun-type counterpart. By symmetrically compressing the fissile material from all directions, it achieves much higher densities and more complete fission of the available material. This results in greater explosive yield relative to the amount of fissile material used. The Teller-Ulam design forms the basis for most modern thermonuclear weapons, revolutionizing nuclear armament through staged compression. Developed by Edward Teller and Stanislaw Ulam, this design uses a fission explosion to compress and ignite fusion fuel, achieving vastly greater yields than fission-only weapons. The primary stage is a standard fission bomb, typically using enriched uranium or plutonium. This stage detonates first, producing intense radiation and heat. The secondary stage contains fusion fuel, usually lithium deuteride, encased in a uranium tamper. This stage is compressed and heated by the primary's energy. Energy from the fission explosion, in the form of X-rays, compresses the fusion fuel inward while heating it to fusion temperatures, initiating the thermonuclear reaction. This design achieves yields in the megaton range, far exceeding fission-only weapons. The fusion reaction contributes 80 to 90% of the total energy output. This cross-section shows the concentric arrangement of components in a thermonuclear weapon, including the fission primary and fusion secondary. Detailed cutaway illustrating the primary fission trigger, secondary fusion device, and the flow of X-rays that initiate the fusion reaction. This diagram provides a comprehensive view of the thermonuclear warhead's construction, highlighting all major components and their roles. The three-step process: compression by radiation pressure, heating by X-rays, and final ignition of the fusion fuel. Comparisons showing the dramatic increase in weapon yields over time, from kilotons in 1945 to hundreds of kilotons today. Nuclear explosions produce catastrophic effects that unfold in distinct phases, beginning with immediate devastation, and extending to long-term environmental contamination. The blast wave is the first and most destructive immediate effect, consisting of a supersonic shockwave that radiates outward from the explosion center. This wave compresses air, creating pressures that can exceed thousands of pounds per square inch, capable of demolishing buildings and causing lethal injuries through blunt force trauma. Thermal radiation follows immediately after the blast, emanating from the fireball as intense infrared and visible light. This heat can cause severe burns and ignite combustible materials, with temperatures reaching thousands of degrees Fahrenheit within the fireball itself. Prompt ionizing radiation consists of gamma rays and neutrons released during the nuclear reactions. This radiation penetrates the body, damaging DNA and causing acute radiation syndrome, with symptoms ranging from nausea to death, depending on exposure levels. Nuclear fallout consists of radioactive particles that condense from the mushroom cloud and are dispersed by prevailing winds. These particles settle on surfaces, contaminating soil, water, and food supplies, leading to prolonged radiation exposure that can cause cancer and genetic damage across generations. Nuclear explosions cause widespread infrastructure damage, with blast waves and fires destroying buildings, transportation networks, and critical utilities like power and water systems. Recovery from such devastation can take years and require massive resources. Human health impacts include immediate fatalities from blast and burns, followed by radiation-induced illnesses and cancers. Environmentally, radioactive contamination disrupts ecosystems, affecting wildlife and agriculture for decades through bioaccumulation in the food chain. Nuclear explosions create characteristic mushroom clouds as hot gases rise and cool, forming the iconic shape. The fireball expands rapidly, producing thermal radiation that illuminates the surroundings. These visual signatures distinguish nuclear detonations from conventional explosions. The historical use of nuclear weapons began with the bombings of Hiroshima and Nagasaki in 1945. On August 6, 1945, the United States dropped an atomic bomb on Hiroshima, killing an estimated 140,000 people. 3 days later, Nagasaki suffered a similar fate with approximately 74,000 deaths. These events marked the first and only use of nuclear weapons in warfare. Following World War II, the Cold War era saw intense nuclear testing by multiple nations. Between 1945 and 1998, over 2,000 nuclear tests were conducted worldwide. Atmospheric tests released radioactive fallout into the environment, while underground tests contained the explosions within shafts drilled deep into the earth. In response to growing concerns about nuclear testing's environmental and health impacts, the Comprehensive Nuclear Test Ban Treaty was established in 1996. This international agreement prohibits all nuclear explosions in any environment. The treaty has been signed by 184 countries and ratified by 170, though it has not yet entered into force, pending ratification by key nuclear states. Nuclear proliferation and control represents the critical challenge of preventing the spread of nuclear weapons to additional nations. Nuclear proliferation involves the dissemination of nuclear weapons technology and capabilities to more countries. This process increases the number of nations possessing these devastating weapons. The Nuclear Non-Proliferation Treaty, signed in 1968, aims to prevent the spread of nuclear weapons while promoting the peaceful use of nuclear energy and working toward global nuclear disarmament. The proliferation of nuclear weapons poses severe dangers, including the potential for these weapons to fall into the hands of terrorist organizations, the risk of accidental detonation, and the heightened possibility of nuclear conflict. International efforts, including diplomatic meetings and agreements, are crucial for controlling nuclear proliferation and advancing toward the ultimate goal of nuclear disarmament. In conclusion, strong international cooperation and commitment to nuclear control measures are essential to prevent the catastrophic consequences of nuclear proliferation and to maintain global security.